everybody. I'm here today to talk softly about space. I got a couple requests and I personally am really into it. I was in the astronomy club in high school. Awesome. And I know it's not everybody's cup of tea, so I apologize if this video isn't for you, but if you have ASMR and you're into astronomy, then I hope you enjoy it. I decided to break it up into 2 parts because there's so much to talk about, and today I'd like to focus on the formation of our galaxy and solar system and take a close look at our planets and our sun, and that's pretty much it. I have some postcards and some articles, maps, and a solar system kit to put together at the end, if time permits, and looks like it shouldn't be too hard. So, just a note on the field of astronomy, it's actually a branch of physics that studies celestial bodies and the universe as a whole, and there's several different sub branches of astronomy. But basically it's the study of the universe, which encompasses all matter. And although it's just a theory, most astronomers agree that the origination of the universe was the Big Bang, and before sound and elements and any atoms even, there was just energy, an unknown type of energy, and it was from this unknown type of energy that the universe was formed. And it was during a massive blast, and the universe began to expand at incomprehensible speeds. Now scientists arrived at this theory partly because they've studied other galaxies, and the galaxies are still moving away from ours, moving away from each other, most of them. Obviously much more slowly now. So it kind of led them to the theory that the universe is expanding and that there had to have been a start to the expansion and the origination of matter and elements, etc., etc. So they devised the Big Bang Theory, and this was about 10 to 20 billion years ago. And after this massive explosion and expansion, there were the formation of elements and cosmic dust and clouds of mostly hydrogen. And these are known as nebulas. Here's a picture of a nebula. Obviously not one of the original nebulas, but a nebula is a cloud of dust and gas from which new stars are created. And there's 3 different types, and we'll talk more about nebulas and stars in the next video. But basically, there was a pre-solar nebula, and that formed our sun, and then a solar nebula that formed our planets. And so that's pretty much the Big Bang was the generator of all mass. And over the next 100 millions of years, stars and galaxies condensed out of different pockets of density and different nebulas and clouds and plasma and all this stuff just floating around, and these mass clouds begin to collapse in on themselves. So our sun was formed by the pre-solar nebula about 4.6 billion years ago. And basically, a nebula is like 98% hydrogen, or this one in particular, and like 2% other heavier elements. So the giant molecular cloud collapsed under its own gravity, and it was this fragment that formed our solar system. Other fragments collapsed to form other solar systems and suns and stars, etc. So as the region that would become our solar system collapsed, the center became white hot, where matter started collecting. This mass of interstellar gas and dust was collapsing under its own gravity, and all this hydrogen was being compressed, and the pressure began to cause the hydrogen to convert to helium in a process known as binary fusion. And this just causes huge amounts of energy. And so the sun, this inner collapsation and compression of hydrogen started to just pull most of the mass of this nebula into it. And to prevent itself from further collapsing on itself, the binary fusion caused such expansive energy that pushing outward that it enabled it to not further fold in on itself, and it eventually kind of became a little bit stable and what is known as our sun now. So basically our sun is just turning hydrogen into helium and expending lots of energy, and it will eventually run out of hydrogen, but not for 5 billion years. So this binary fusion warms our planet, and that's pretty cool. So that's pretty much, so the collapse of molecular clouds vaporized, and the fireball expanded and then eventually became stable. Most of the collapsing mass from the nebula gathered in the center, and then what was left flattened into protoplanetary disk of mass that rotated around the sun, what became the sun, a protostar, which is now a main sequence star. And we'll talk about the life cycle of stars also. So the planets and asteroids, comets, other solar system bodies, moons, were formed from what was left of the collapsing matter. And they were left to orbit the sun, and then there were just particles of heavier elements that were left, and they collided with each other, and they kept colliding, and they formed bigger bodies, and till we had planets, or really large bodies circling the sun. So the 4 inner planets, Mercury, Venus, Earth, Mars, they're terrestrial, and they're not. The other 4 are the gas planets. The 4 inner planets closer to the sun, it was too hot for gas to form a planet, so those were formed from trace elements like iron, nickel, aluminum, some silicates, and so they're solids and terrestrial and smaller because there weren't very many elements of that nature. The 4 gas planets, they formed and past the frost line where gas could be vaporized and turned into ice, and they're immensely larger than the other planets. And I have a map to show you just exactly the difference. this is like to scale, and it shows you the 4 smaller planets down here: Mercury, Venus, Earth, Mars, and then look how big Saturn is in comparison. That's pretty intense. So this shows, and then you have Neptune and Uranus, and Jupiter is the other large one. And then you have the small terrestrial planets over here. And this map says, born in the darkness of interstellar space some 4.6 billion years ago, our solar system emerged from a contracting molecular cloud of dust and gas. When the core of this cloud became dense enough, gravity triggered the collapse of its inner layers. Matter fell inward for perhaps 1,000,000 years. Internal heat trapped by the gases fired up a protosun and ignited thermonuclear reactions. Rotation drew the material into a swirling nebular disk. Its hot innermost constituents drifted further inward, enlarging the protosun. A powerful gaseous outflow from the solar inferno blasted away the infalling material, unveiling our newborn sun in all of its brilliance. The cooler, more distant portions of the nebula contained the raw material of a planetary system. So, what didn't form into planets? What like rocky substituents that didn't form into planets left behind that are small fragments of what could have formed planets are the asteroids. And they're mostly found between Mars and Jupiter in the asteroid belt. And comets are typically found a comet out where the icy giants are. A comet consists of a tiny, irregular shaped nucleus and extended atmosphere known as the coma, and often a long tail of gas and dust. A passing star or molecular cloud can disturb the orbit of a comet, bringing it nearer the sun. It then begins to vaporize, and this actually makes it turn into those pretty colors, or makes it visible to us. So, pretty interesting. And then this just shows another scaling of the 4 terrestrial planets in comparison to size to the 4 large planets. So, pretty drastic difference. Pretty awesome. Okay, so that just kind of sums up how everything is formed and our planets formed. Now, most of our planets have moons, and moons have come to exist 3 different ways, scientists believe. One of them is co-formation from a circumplanetary disk, and so they kind of formed with the planet, and that's really only typical in the gas giants. Another is through impact debris, such as an asteroid or meteorite hitting and sending a chunk of the planet into orbit around itself. And that, for example, is how we believe to get our Earth's moon, our one and only moon, or capture of a passing object, and so pulled into the gravitational force of that planet. So that's pretty much all I have to say about our solar system as a whole. If you have any questions, feel free to ask me. I try to explain it in terms that were easy to understand. I think I already said this, but basically, there are still nebulas today, and when we see, say, pre-solar nebula or solar nebula, or the rest of the nebula that form the planet, it basically is just a cloud of gas, and I think I read that on the card, so there are still nebulas today, and those are one of my favorite things to look at, and we'll look at those in the next video. Now we're going to move on to the individual planets, and I'm going to briefly go through and show you a picture and discuss its main features, and then we'll build some together. So let's start with Mercury. Mercury is the smallest. It's closest to the sun. This is a picture of it. It is the fastest, rotating this way on its axis and around the sun. It rotates around the sun in 88 Earth days. It has no atmosphere, so its temperatures can vary from a high of 800 degrees Fahrenheit to negative 280 degrees Fahrenheit. So that makes it impossible. With no atmosphere, there's obviously not going to be much on it. That's Mercury. Venus. Venus is similar in size to Earth. The second planet from the sun. Water vapor is present. It does have an atmosphere, but its atmosphere is so thick and rapidly spinning, it creates a scorched world with temperatures hot enough to melt lead and a surface pressure 90 times that of Earth. It's a toxic atmosphere of carbon dioxide, clouds of sulfuric acid, trace amounts of water. So the thick atmosphere traps the sun's heat, and there's all kinds of reactions and things going on. It rotates around the sun in 240 Earth days. Venus. And my favorite, Earth. Little partial to it. Earth. So amazing. Such placement and just everything about it enables life and us to live on it. It's so cool. The atmosphere is the perfect size, not allowing things to escape, but not trapping in too much heat. And most importantly, this enables for water to exist, and water gives life. So, the living planet. And so we have a protective atmosphere, temperature pretty narrow in comparison to the other planets, formed 4.6 billion years ago, has one moon, thought to be believed from an asteroid, nickel iron core. Like most of the terrestrial planets, there's volcanoes, because most of the terrestrial planets, all four of them, have nickel and iron in cores that are near the sun, and when they formed, they were like molten lava. There's a lot of volcanic activity and such on the four planets, including Earth, and a lot of movement of the land and change and things inside of the Earth, and so that's pretty cool. But the nickel iron core is so important because it gives the Earth a magnetic field, and I think from impact from the asteroid that formed the moon, the Earth is knocked in a tilt, and because of this tilt and the nickel core and the rotation of the Earth, this magnetic field keeps us safe from solar flares and solar wind, which is so important. because if we weren't protected from them, we would scorch to death. So I think that's incredibly interesting. And sorry for the noise of the cars driving by. I'm actually in the middle of nowhere and there seems to be a lot of activity today. So that pretty much sums up Earth. One cool thing I will say is that where the magnetic field weakens around the poles, sometimes the solar wind does get into the atmosphere just a teeny bit, and it's known as the aurora borealis. And the aurora, I forget what the other pole calls it, and it's a spectacular light show, and it's basically solar winds from the sun entering the atmosphere where the magnetic field is weakened. So I think that is really cool. It's something that I would love to see one day. So, Mars. Could there be life on Mars? Could humans ever move to Mars? There's a lot of debate about that. Its surface has been changed by volcanism, I don't know. Volcanoes, we'll just say. Excuse me for my moment of stupidity. Impacts from other bodies, movement of its crust, and other atmospheric effects such as dust storms. There are polar ice caps that contain water, but most of the water has pretty much been turned to ice or evaporated. The atmosphere is too thin, really, so it's not really feasible to think about living there yet. There's still so much research. So there's thought to be once a great flood on Mars, but all that water has disappeared. And it takes 687 Earth days for Mars to rotate the sun. Jupiter. Here's a picture of Jupiter. And that's the only picture I have of Jupiter. It is the 5th planet from the Sun. Its rotation period around the Sun is 4,333 Earth days. Largest planet in the solar system, composed of mostly helium and hydrogen, has 16 moons. So, most of the terrestrial planets, their atmosphere is made by carbon dioxide, except for Earth, it's nitrogen and oxygen. And then when you get out to Jupiter, you start to see a lot more hydrogen, helium, and methane. So that's like a huge difference. Jupiter, Galileo saw Jupiter. I think he also looked at the sun too long and went blind. Was that Galileo? I think it was Galileo. So, numerous small outer moons are believed to be asteroids captured by the giant planet's gravity because it's so huge that any asteroids that venture too close to it are just pulled into orbit. The atmosphere is similar to the Sun. It has a magnetosphere with charged particles. Its moons are embedded in an intense radiation belt, and it has rings. I'm going to talk about its rings. Most visible clouds are composed of ammonia. The giant red spot is a giant storm, and because Jupiter spins quickly and there's no land masses to stop the storm, it's just continuously going. Oh yes, it does have rings. They weren't discovered until 1979. And it's most known for its rings is Saturn. That's another picture of Saturn. I like this one. It's so cool. Its atmosphere is hydrogen and helium. 6 planet, 10,759 Earth days to rotate. Has a small, solid core and a gaseous surface, like Jupiter. The rings are extremely thin. Once thought to only have 3 rings, it has been discovered that there are literally thousands of them, and they're composed of silica rock, iron oxide, and ice. So, that's pretty cool. It's the most extensive and complex ring system in the solar system, expanding thousands of kilometers from the planet. And yeah, pretty cool. Moving along, we have Uranus. Oh, just one picture of that. And this is Uranus, and it's also hydrogen and helium atmosphere, but it has a lot of methane, and that gives it its beautiful blue-green appearance. 7th planet from the Sun. Rotation period is 84 Earth years. Gaseous planet. This right size is color enhanced to bring out detail in the polar region. It is off kilter. Its rotation is nearly horizontal, like it's been knocked on its side, and its magnetic field is tipped over, so it experiences seasons that last over 20 years. Uranus. And last but not least, because Pluto is not a planet anymore, I hope everybody watching this knows that. If not, now you do. Neptune. Hydrogen, helium, and methane atmosphere. 8th planet in the solar system. Rotation is 60,189 Earth days. Radiates more heat than it absorbs, and has a greater density and mass than Uranus. So, Neptune. That's all there really is. Neptune's magnetic field is also tipped over by about 47 degrees. Like Uranus, whose magnetic axis is tilted about 60 degrees. Neptune's magnetosphere undergoes wild variations because of the misalignment. There's a mystery storm. It was there and then it wasn't, and then there was another one and then there wasn't. Scientists are still studying that. So, Neptune. That's it for my pictures. As well as my postcards. I will show you one cool thing before we move on. And that is solar superstorms. Since we're talking about the sun and Earth's protection from solar flares, sunstruck. The space weather forecast for the next few years. Solar storms with a chance of catastrophic blackouts on Earth. Are we prepared? When was this written? June 2012. This shows most flares in coronal mass ejections. More may be headed earthward. And they're basically solar storm, an aurora. Doesn't say which pole it's on, it just says an aurora. This is what it looks like. Pretty cool. This shows what causes the auroras, the magnetic field, and what happens when it breaks through. June 7th, 2011, the Solar Dynamics Observatory captured a coronal mass ejection at 4 o'clock. Using different wavelengths of light that reflect temperature and layers of the sun's atmosphere. Why the sun's atmosphere gets hotter further from its surface remains a mystery. Regions with the corona can rise to more than 10 million degrees. In 1859, the solar superstorm. Charged particles set off intense auroras over much of the earth. Some people thought their cities had caught fire. Plasma loops, wide enough to encompass many Earths, are caught in profile on the edge of the sun, while a wave-like prominence above the loop slings charged solar particles into space. Scientists tune in to solar sound waves to detect active regions days before they bubble up to the surface, but there's no way to stop them. There's the loops and the waves. It's really hard to say about solar flares. I don't want to buy into getting petrified about solar storms reaching the earth and causing catastrophic blackouts. So now we're going to look at the solar system. And I'm going to move it down so you can, there we go, see what I'm doing. We have bugs in here, not real bugs. My niece needs to put this in here. I do need it. This must be Saturn, Jupiter, Uranus, Neptune, Mars, Earth, Venus, Mars, Mercury. Mercury's supposed to be smaller. You know, Mercury's more like this color, so we'll say this one's Mercury. Okay. Centipede. Not supposed to be there. Okay. Let's see, how do we do this? Looks like we've got the sun. And the sun needs I may need to pause this and go get some scissors. consists of a center star, the Sun, and the 8 planets that orbit it. It's part of the Milky Way galaxy, which also encompasses globular clusters, nebulas, other stars, no other planets. So our solar system is our planets and our sun, but the galaxy that we live in is like includes the other, all the other stars and etc., etc. Okay, so this just shows that this is really complicated actually. Tie one end of the thread to the whole of the paper boards and the other end to the hanging surface. And then how do you hang? Oh, okay. No. So one's gonna hang off this edge. This connects all of them. One's going to hang off this edge. But how do these hang through? Is there a hole that it's too dark for me to see? How do you get Mercury to hang from the middle?